So let's draw a unit circle. And we'll recall that on the unit circle, if we have a point P, X, Y, that corresponds to some angle. And so you have cosine of theta, sine of theta. What we're going to do here is we're going to define two angles, an angle U and an angle V, and they're arbitrary. So I'm going to place angle U over here somewhere. So this is angle U, and then I'm going to define a second angle, angle V. And I'm going to define the coordinates for angle U as U sub 1 dash U sub 2. Again, from what you know about the unit circle, U sub 1 is going to be cosine of U, and U sub 2 is going to be sine of U. Then, same reasoning we have for V, V sub 1, V sub 2, where V sub 1 equals cosine of V, and V sub 2 equals sine of V. Well, using the angle addition postulate, V plus this angle adds up to U, and then by doing subtraction, I get the angle U minus V right there. Okay? There's the angle U minus V. Let me erase this little arbitrary angle that I drew in here. That was kind of a review or a setup. From geometry, I know that in the same circle or congruent circles, congruent arc lengths form congruent central angles. So I can define another angle, call it W, where W is congruent to U minus V. So I'm going to, for the angle W here, I'm going to label the points W sub 1, W sub 2, where angle W is congruent to angle U minus V. So here we have W sub 1 equals cosine of W, W sub 2 equals sine of W. Well, let's think about this. W sub 1 is cosine W, W sub 2 is sine of W, and the angles are congruent. Well, if the angles are congruent, then so are their trig values. So it would follow that cosine of W would be equal to cosine of U minus V. And sine of W would be congruent to or equal to sine of U minus V. Well, great. That doesn't give us much anything. Real fun. So how do we deal with this? Well, let's go back to geometry, chapter 10. If you'll recall, in chapter 10, if two angles on a circle or two arcs on a circle are congruent, then so are their chords. Well, if two chords are congruent, then they have equal lengths. So let's use the distance formula to describe the distance from here to here, which we know has to be equal to the distance from there to there. So let's go ahead and write that. Let's call this point U, let's go capital U, capital V, capital W, and let's just name this point A. It's a beautiful thing. So the distance squared, and I'm going to square because I don't like radicals, right? The distance squared from U to V is going to equal the distance squared from A to W. It's not root beer, it's just the distance from A to W. All right, so let's go ahead and define it. So change in x squared gives me U sub 1 minus V sub 1 squared. Change in y is U sub 2 minus V sub 2 squared. Change or distance from A to W is W sub 1 minus 1 quantity squared. And then w sub 2, the quantity squared. Now let's see what happens here. Expanding, I get u sub 1 squared minus 2 u sub 1 v sub 1 plus v sub 1 squared plus u sub 2 squared minus 2 u sub 2 v sub 2 plus v sub 2 squared. Beautiful thing. Then I square on the other side, expanding, w sub 1 squared minus 2 w sub 1 plus 1 plus w sub 2 squared. Very interesting. What do these variables represent? Well, u sub 1 was cosine of u. V sub 1, or u sub 2 rather, was what? Sine squared of u. So if I look at u sub 1 squared plus u sub 2 squared, what I really have here is cosine squared u plus sine squared u. And you're saying, oh boy, oh boy, oh boy, oh boy, aren't I happy that I know my fundamental identities? Because we all know from the fundamental identities that for any angle u or theta, cosine squared plus sine squared equals what? Jesuits number 1. It equals 1. So I can do some replacing. I can do some regrouping and substitution. Right there, that equals 1. I can do the same thing. Whoops. Grouped the wrong thing. U sub 1 squared plus u sub 2 squared equals 1. I can do the same thing for the v's. V sub 1 squared plus V sub 2 squared equals 1. Moving over to the other side, I've got W sub 1 squared plus W sub 2 squared equals 1. So, combining like terms, I get 2 for the 1 plus 1 here, 2 minus the quantity, 2 U sub 1 V sub 1 plus U sub 2 V sub 2, better put a 2 there. Everybody see why I put the plus sign inside? Because these were both negative, and I have the negative outside the brackets. Equals 1 plus 1 is 2 minus 2 W sub 1. The 2's get hi-ya, hi-ya. We got rid of them. I also have a negative 2 here, and let's factor out that negative, or the 2 out, and I get U sub 1 V sub 1 plus U sub 2 V sub 2 equals negative 2 W sub 1. Hi-ya! 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 And look what I'm left with, guys. W sub 1 equals U sub 1 V sub 1 plus U sub 2 V sub 2. Now you're going, man, what the heck is that? Well, it's beautiful is what it is. Because if I go back up here and I look at how I defined W sub 1 and how I defined U sub 1 V sub 1 and U sub 2 V sub 2, I can now substitute into this expression and I get cosine of U minus V equals cosine of U, cosine of V plus sine of U, sine of V. Wow! I have derived the first addition subtraction formula for trigonometry. Isn't it a beautiful thing? Man. It's like poetry in a mathematical sense. So then we derive the cofunction formulas. So why or how can I use them to derive more identities? Because I got one. I don't want to have to do this over again for another trigonometric derivation. There must be an easier way. Well, thanks to the cofunction formulas, yes there is. You almost thought I saw a dirty word there, but I didn't. All right, here we go. Remember, we have the fundamental identities from